Charcoal, which is almost pure carbon, is one of the oldest and most versatile materials created by humans. Its history spans millennia, and its uses range from forges and home barbecues to high-tech filtration systems and ferroalloy production. Despite its apparent simplicity, the production of high-quality charcoal is a complex, controlled process of thermal decomposition of wood in the absence of oxygen, known as pyrolysis. This process extracts concentrated energy from wood while removing volatile compounds and moisture. In this article, we will examine in detail the chemical basis of this transformation, trace the evolution of technologies from primitive pits to modern automated retort furnaces, and analyze how the properties of the resulting charcoal determine its application in a wide range of human activities, from cooking to industry. Charcoal production isn't simply burning wood. It's a controlled process of thermal decomposition of organic materials in an oxygen-free or low-oxygen environment, known as pyrolysis or dry distillation. The goal is to break down the complex polymers that make up wood and remove volatile components, leaving behind a concentrated carbon matrix. Raw wood consists of three main polymeric components: cellulose, hemicellulose, and lignin. Each of these behaves differently when heated. The wood pyrolysis process can be divided into several key stages, which occur as the temperature inside the loaded wood increases. The first stage is drying. When heated to 150 degrees Celsius, the hygroscopic moisture evaporates from the wood. This stage involves no chemical changes, but is critical for the effectiveness of subsequent pyrolysis, as water evaporation requires significant energy. The second stage, beginning at 150, 200 degrees C and lasting up to 280 degrees C, is endothermic decomposition, or pre-pyrolysis. The wood begins to slowly char, releasing non-condensable gases such as carbon monoxide and carbon dioxide, as well as acetic acid and methanol vapors. At this stage, the least thermally stable component, hemicellulose, primarily decomposes. The third and main stage is exothermic pyrolysis, occurring in the range of 280 to 500 degrees Celsius. This is where the most intense and violent reactions occur. Cellulose, the main framework of wood, decomposes at the fastest rate, generating a large amount of heat. Lignin, the strongest polymer, decomposes more slowly and over a wider temperature range, up to 700,000 degrees Celsius. At this stage, the majority of volatile products are released. Pyrolysis gases, consisting of hydrogen, methane, carbon monoxide, and other hydrocarbons, as well as a liquid condensate known as slurry, or wood vinegar, which contains acetic acid, methanol, acetone, and a complex mixture of organic compounds. It is the removal of these volatiles that transforms brown wood into porous black charcoal. The fourth stage is roasting, or calcination, at temperatures above 500 degrees Celsius. During this stage, residual volatiles and resins are removed from the formed carbon skeleton. The higher the final pyrolysis temperature, the purer and denser the resulting coal, with a higher specific heat of combustion and a lower volatile content. Coal obtained at 350 degrees Celsius will be light, brittle, and resinous, while coal calcined at 800 degrees Celsius becomes hard, dense, and produces a metallic ringing sound when struck, a quality highly valued in metallurgy. The key to successful pyrolysis is strictly limiting oxygen access. If oxygen enters the reaction zone, the carbon in the matrix oxidizes to carbon dioxide, resulting in conventional combustion, leaving behind only a handful of ash instead of charcoal. Therefore, all production technologies, from the ancient pit to the modern retort, boil down to heating the wood through external or internal partial combustion, but preventing oxygen from directly contacting the bulk of the wood in the pyrolysis zone. Understanding this chemical principle allows us to evaluate the evolution of technologies aimed at increasing char yield, quality control, and the utilization of valuable pyrolysis byproducts. Before becoming an industrial product, charcoal was produced for thousands of years, using methods based on a deep empirical understanding of pyrolysis. These methods, despite their apparent simplicity, required the highest levels of skill, intuition, and attention to detail from the charcoal burner, as the entire process was controlled visually and through indirect means. Their efficiency was low, and their impact on the environment and human health was significant, yet they provided civilization with charcoal until the early 20th century. The most ancient and primitive method is pit charcoal burning. This method was widespread throughout the world, from Europe to Japan. The technology involved digging a round hole in the ground or using a natural depression. A small fire of small pieces of wood was lit at the bottom of the pit, serving as the igniter. The pit was then tightly filled with carefully stacked logs of a specific species and size. Most commonly, hard woods, such as oak, beech, hornbeam, and birch. The stacked wood was covered with a layer of damp grass, leaves, or moss, and then covered with earth, leaving only a few small vents for smoke to escape and control the process. Pyrolysis began at the igniter and slowly spread throughout the pit. The charcoal burner had to constantly monitor the color and character of the smoke coming from the vents. Thick white smoke indicated the drying and moisture evaporation stage. Yellow smoke indicated the beginning of active pyrolysis and resin release, and a transition to a bluish, almost invisible smoke indicated the completion of the main reactions. Then the vents were completely sealed to block the oxygen supply and halt the process. The mass inside slowly cooled for several days. The charcoal yield was only about 15–20% of the original wood mass, and the process was extremely lengthy, up to several weeks. The charcoal quality was often uneven. Some wood might not undergo complete pyrolysis, while others would turn to ash due to localized oxygen exposure. A more sophisticated and widespread technology, until the middle of the last century, was the heap or pile charcoal burning method. Instead of a pit, the wood was stacked directly on the ground in a large hemispherical or cone-shaped pile. The base of the pile consisted of a vertical ventilation shaft of logs, around which the bulk of the wood was carefully placed, bark side down, forming the so-called pyrolysis chamber. The logs were stacked as tightly as possible to minimize air gaps. The pile was then covered on top and sides with an insulating layer, first with spruce branches or straw, and then with a thick layer of turf, earth, and coal dust, creating the so-called jacket. This shell had to be airtight to prevent air from penetrating. The process also began with ignition through the top shaft. The fire gradually descended, and as it moved, pyrolysis began in the upper layers. The master charcoal burner, monitoring the smoke and temperature, regulated the process by opening or closing special exhaust ducts at the bottom of the pile. The entire combustion and pyrolysis process of a huge pile, reaching 10 to 12 meters in diameter, could last from 10 to 30 days, and cooling took even longer. The charcoal yield was higher than in a pit, reaching 25–30%, and the quality was more consistent. However, this method was extremely labor-intensive and required constant monitoring of the pile day and night. It was also notorious for its devastating impact on surrounding forests, as burning a single pile required a huge amount of wood, and vast areas were burned. A more localized and controlled option was charcoal burning in earthen or brick barrel ovens. Essentially, this was a transitional form to stationary ovens. A large metal barrel or a simple brickwork structure with a chimney and ash pit was filled with wood, sealed with a lid with a small hole, and heated over an open fire. A lack of oxygen inside the barrel led to the pyrolysis of the wood. This method was faster and required less skill, making it popular for small-scale and artisanal production, especially in regions with wood shortages. However, the charcoal yield and quality remained low, and the process was fire hazardous and toxic due to the uncontrolled release of pyrolysis gases directly into the atmosphere. All of these traditional methods shared fundamental flaws: extremely low wood utilization rates, colossal emissions of harmful substances into the atmosphere, including methane, carbon monoxide, and tar, high dependency on human error and weather conditions, and the danger of forest fires. Nevertheless, these archaic technologies provided humanity with coal for centuries to smelt metals, heat homes, and cook, laying the foundation for the subsequent Industrial Revolution, which in turn required other, more advanced methods of producing this critically important material. The inefficiency, environmental harm, and unpredictable quality of traditional methods have led to the development of modern industrial charcoal production technologies. Their goal is not only to maximize the yield of a high-quality product, but also to fully control the pyrolysis process, minimize emissions, and utilize or recycle the byproducts of wood decomposition. Modern methods can be divided into two broad groups: batch and continuous, with the key element in both cases being the use of specialized furnaces called retorts. The most common technology for producing high-quality coal worldwide today is pyrolysis in stationary vertical or horizontal retort furnaces with batch operation. A retort is a sealed metal or refractory chamber loaded with wood. The retorts are installed in a common furnace where they are heated by external heat sources, such as hot gases from the combustion of a portion of the pyrolysis gas or another fuel. The wood inside the retort is heated through the walls, but is not exposed to open flame or oxygen. As it heats, the wood begins to release volatile substances, which are removed through a system of pipes into separate condensers. Here, they are cooled and separated into liquid products, the so-called slurry, or wood vinegar, and wood resin, and non-condensable pyrolysis gases. These gases, consisting primarily of hydrogen, methane, and carbon monoxide, have a high calorific value. The key advantage of modern installations is that these gases are not released into the atmosphere, but are fed back into the furnace to maintain the pyrolysis process, creating a virtually self-sufficient energy cycle. After the pyrolysis cycle is complete, which lasts from 8 to 20 hours depending on the retort volume and the type of feedstock, heating is stopped. The retort is disconnected from the gas line and allowed to cool slowly, sometimes in a special airtight chamber to prevent spontaneous combustion of the hot coal. Only after complete cooling is the coal unloaded. This method ensures a high and stable coal yield, up to 35 to 40% of the mass of absolutely dry wood, and allows for the production of coal of a specified quality by controlling the temperature and process time. Furthermore, it allows for the collection and processing of valuable chemical products from pyrolysis. Continuous pyrolysis technology is more advanced and cost-effective in terms of productivity. In such units, such as auger or drum-type units, raw materials, chips, sawdust, or small wood waste are continuously fed into one section of the reactor, slowly moving along it as it passes through the heating, pyrolysis, and cooling zones, and the finished charcoal is continuously discharged from the other end. Heating is also achieved by burning pyrolysis gases. Such lines offer high productivity, maximum energy efficiency, and full process automation. However, they are more often used to process finely dispersed raw materials into so-called briquetted coal, where coal dust is pressed using binders, or for the production of industrial coal, where absolute homogeneity of the lump product is not critical. Continuous production is less suitable for producing classic lump coal from logs due to the difficulty of uniformly heating large fragments. A separate area is the production of activated carbon, which is a two-stage process. In the first stage, ordinary charcoal is produced. It is then activated, treated with superheated steam or chemical reagents, at temperatures of 800 degrees Celsius. During this process, some of the carbon is burned off, and a highly developed network of micropores forms on its surface, greatly increasing the specific surface area and adsorption capacity of the material. Such units represent the pinnacle of the process chain and are considered high-tech chemical production. Modern technologies also place high demands on raw materials. Specially harvested hardwoods, such as oak, beech, acacia, hornbeam, and birch are used. Softwoods are used less frequently, as their high resin content produces charcoal with a high content of volatile compounds, which sparks and has a distinctive odor. Raw material preparation includes chopping, splitting into standard-sized logs for uniform heating, and mandatory drying to a moisture content of no more than 15–20%, which dramatically improves pyrolysis efficiency and the quality of the final product. Thus, the evolution of technology from a steaming earthen pile to a computer-controlled retort furnace with a gas recovery system is a journey from craft to precision engineering. Modern production has solved the main problems of the past. It is environmentally friendly, thanks to a closed-loop process, economical due to the use of its own gases, and predictable in quality, allowing charcoal to be used, not only for barbecue, but also in the most demanding industries. But it's important to remember that charcoal, a product of deep thermal transformation of wood, acquires a unique set of physical and chemical properties that determine its wide range of applications. These properties directly depend on the source wood species, temperature, and duration of pyrolysis, allowing for the creation of different grades of charcoal for specific applications. Understanding this relationship is key to understanding why this ancient material remains indispensable in the modern world. The key properties of charcoal stem from its porous carbon structure. First, it has a high specific heat of combustion. High-quality charcoal, calcined at a high temperature, produces more heat during combustion than the original wood, approximately 31 mJ/kg versus 15–18 mJ/kg for dry wood. This is due to the removal of moisture and volatile compounds, which concentrates the energy in the carbon matrix. Second, it burns flameless and with minimal smoke, as the primary combustible gases have already been removed during the pyrolysis process. This ensures a stable, even heat, ideal for precise temperature control. Third, it has a low ash content, only 1–3% for pure wood charcoal, minimizing waste. But perhaps its most valuable property is its high adsorption capacity due to its developed microporous structure, which works like a sponge for gas molecules and dissolved substances. These properties dictate its primary modern application. Its most widespread and visible use is as a fuel for grills and barbecues. Here, key parameters include not only calorific value, but also burn time, ignition speed, and the absence of sparks. Special grades of hardwood are produced for this purpose. Oak and beech charcoal produce a long, stable heat, while birch charcoal, although higher in volatile matter, ignites faster. Briquettes, pressed from fine coal with natural binders, have become a popular form. They ensure a predictable shape, consistent burn time, and consistent temperature. In industry, charcoal has equally important, albeit less noticeable applications. In metallurgy, particularly in the production of high-quality steels and ferroalloys, it is used as a reducing agent and alloying additive. Its advantage over coal and coke is its extremely low sulfur and phosphorus content, which are harmful impurities for metals. In the chemical industry, it serves as a raw material for the production of carbon disulfide, calcium carbide, and activated carbon. As an adsorbent, it is indispensable in purification systems. Activated carbon is used in water and air filters, gas masks, medical hemosorption devices, and in the food industry for the purification of sugar, alcohol, and oils. Its porous structure traps pollutant molecules, heavy metals, chlorine, and organic compounds. In agriculture, crushed coal is used as a valuable feed supplement for livestock and poultry, improving digestion and absorbing toxins. It is also included in soil substrates and fertilizers, where it acts as a structure-forming agent and nutrient accumulator. Modern charcoal grades are often labeled by their intended use: premium grill, restaurant, technical, hookah, and activated. Each grade is the result of a production cycle optimized for specific requirements. For example, hookah charcoal must smolder at a very low temperature without emitting carbon monoxide, and is typically made from coconut shells through low-temperature pyrolysis rather than wood. Thus, we see that charcoal is more than just a black fuel. It's a highly functional material whose properties, from thermal engineering to sorption, make it a critical component in a wide range of applications, from leisure and cooking to high-tech processes in metallurgy, chemistry, medicine, and ecology. Its versatility and ability to be produced from a renewable raw material, wood waste, guarantee its sustainable place in humanity's technological chain in the future.